Hi guys, Paul from Viezu here. Joining me again is Simon as always.
Hi everybody.
Welcome to our October webinar, and we've got another full session planned for today. So if you joined us in last month's session, you'll know we concentrated on the Alientech ECM software and we were looking at the creation of a diesel map. Well, today we're going to move on to a gasoline map. Simon, what have you got lined up in today's session?
So keeping it on the Volkswagen Audi group as we did last time with the diesel, we have an Audi S3 2-litre TFSI engine.
Okay, really popular vehicle for tuning.
Very popular vehicle for tuning. This ECU covers across, again, a wide range of the gasoline engines. It's on a Bosch format, again, one of the biggest ECU manufacturers in the world.
Yeah.
And the information and logic we're going across today can be applied to a wide range of vehicles. Not just Volkswagen Audi group, but Fiats, Ferraris, Mercedes, and everything around that as well.
Okay, so we're going to go creating a map literally from scratch, stage one map all the way through. Okay, great. So last session literally was a full hour when we did this on a diesel. We're going to try and keep on time, but it will be probably a full hour again today. So get your notepad ready, get your pen ready, make sure you've got a coffee or a water or whatever you need. We will try, as always, to impart as much information as we can, and we'll also, because this is a live session, we'll try and take any live questions if you've got them as we go. Obviously, we need to keep questions a little bit on track, if you like. If you've got questions that are falling out of the scope of today's session, we'll either try and cover them at the end or we'll drop you an email afterwards, but we'll try and pack in as much as we can in today's session. Before we do that, I want to do an absolute shameless plug. We are on the eve of SEMA, of course, just in 2 weeks' time. In fact, 2 weeks today, SEMA's show opens. We will be at SEMA. If you're attending, we would love to see you. We've got some very special show offers on. If you can't get to the show, email us show week and we will also try and share those special offers with you. If you can get to the show, we would love to see you. Yep. We've got most of the mainstream European tuning tools on stand. We've got the KES, the Auto Tuner, who else have we got? We've got B-Flash on there, there's Magic as well, of course. So most of the tools there, but we've also got the map writing software, and we will be doing on-stand demonstrations of the map writing software. So you can come and meet one of the trainers and talk to us about, you know, any problems you've got with solving that with the software that you need advice on, or if you're looking to purchase software, we can talk to you about which one might be the best fit for your business. And as well as that, we are training around SEMA as well. We've got a 3-day EVC course at the end of the SEMA show, so that's on the Saturday, Sunday, Monday, and leading up to SEMA opening, we've got a 3-day EVC gasoline course. The diesel is pretty much full now. There are some spaces left on the gasoline. Get in contact with us if you'd like to come and attend a training course around SEMA. But that's probably enough of me prattling on with the shameless plug. Let's get map writing. Simon, what have you got for us?
Okay, so in a similar way we did with the diesel ECU that we did in the last webinar last month, we've got our driver opening ECM Titanium for our 2-litre TFSI engine here. Now, as I've already mentioned, the logic we're going to be going across today, the strategy and approach to the tuning is the same strategy and approach we would apply to all gasoline vehicles, whether it's turbocharged, supercharged, or naturally aspirated. Now, obviously, as you can see on the screen here, there are quite a few maps in this driver, actually more than we had in our diesel driver last month in the diesel webinar. We're not going to look at every single map in the driver because, again, if you attended last month's webinar, you'll know we don't need to modify every map, and not every map table inside of the ECM driver is required for a typical stage 1, safe stage 1 performance tune. There are a lot of additional features in this driver, and I'll highlight just one now just to show. We've got within our fueling system, we have elements for the fuel pump calibration. So if you're fitting a higher pressure fuel pump, so a common upgrade on these vehicles and many high performance petrol vehicles, really sort of getting into stage 2/3 tuning and beyond at that point, you have the ability to calibrate the fuel pump. We've also got your typical noisy overrun maps. So if you're looking at changing things popping and banging and crackling and burbling and all the other descriptions for them in the ECU driver as well.
And we'll get a chance to get into those maps a little bit today?
We'll touch upon a couple of those today. Yeah. Obviously the focus and key for today is going to be the stage 1, safe stage 1 performance tune. Effectively, how we can unlock the secrets of this ECU to take it from the stock performance levels to a safe stage 1 or performance tune level using the data that's inside of the ECU. Obviously, in the real world, you'll need to apply data logging and validation to your tuning. So testing on the dyno where you can, or in safe off-road controlled conditions if you're road testing, of course. But that data logging is key to ensure that the changes you've made are having the desired effect that you want upon the car.
Makes sense.
So just as you can see on the screen there, we've got things like fuel pump, that can be adjusted as well. So a whole range of additional maps, functions in there with the square radius of the piston. Anyone that's fitted a high pressure fuel pump will know that's a very, very important map, and something that didn't used to be in the ECM drivers many years ago.
The ECM drivers have got quite a lot better though, haven't they? Not been rude, it's great software, but years ago they were quite crude. I think they've got much, much better. That's my understanding.
Oh, the depth of detail into some of the drivers now is really, really strong. It was very much a stage one sort of only piece of software many years ago. I think we'd all agree putting high pressure fuel pumps on is not a stage one performance tune. It is far beyond that, and you can see from the driver a number of the maps have now been added into it. And it is one of the really key features with ECM and with Alientech support. If you're looking for a particular map type or something you need adding into the driver, you can message their support with the driver details and say, hi, can't find this, can you please add it into the driver? And the team will look at developing that for you.
And when they do that, it's then available for everybody going into that software again in a future time. So you're not just making improvement for yourself, you're improving the driver for all the users.
Yeah, and as tuners, we're all helping ourselves within the community here. So if someone else requests a particular map for you, that means that you've got it in the driver when you go to use it in the future as well. So we all help each other to improve the quality of the drivers and the data that's available there. So, conscious of time, we're going to jump into the driver now, and we're going to go through the investigation phase of the webinar itself, where we're looking at the values inside the maps to understand the stock data, and starting to see those little clues and tips as to how much further we can push the ECU safely for our stage one performance tune. Now, you can look at all of the data on the screen here, and you can easily get lost. There's a lot of information inside of the ECM Titanium driver. When it comes to a gasoline engine, the first place we'll typically start is going to be with our requested engine load map. And that's one of the maps that's controlling the amount of air that we're requesting into the engine. If you were tuning a diesel, it's a bit like your torque request map or your fuel request map. Now, one of the key things to note here is we do have engine torque maps. We have an entire folder of them, but this ECU runs what's called an air-based strategy. So the primary driving force for this engine, this ECU strategy, is going to be air-based. You'll see through different ECUs, through different manufacturers, depending on the year of the vehicle and the ECU type itself, that they will shift from the air-based strategy to a mix of air and torque-based strategies, to then the very latest, I think your 2020 CMOS 19s, Bosch MG1 ECUs, where they still have air-based maps, but the primary control is torque. It all runs from a torque-based strategy. Basically, as anyone's familiar with who's been in the industry for a long time, gasoline and diesel ECUs have become closer and closer together with their format, their logic and their strategy. So let's get into the first map table and let's see what the vehicle's actually requesting. So that's going to be our requested engine load map, that's a percentage of air. Left-hand side we have our RPM, and across the top we have a percentage value. Now this is actually torque. On a number of the ECUs, everything from your late 90s through to your mid and late 2000s, even into the early 2010s, it was measured torque as a percentage. So we didn't really have Newton meters coming into the control strategies at this point. It was all based on a percentage of a calculated amount of torque. As a tuner, we can apply quite simple logic here and see if we have effectively 0 to maximum torque as a percentage, it's a little bit like your throttle. If I've got 50% pedal, I'm probably going to have about 50% of my torque. Now, that's not a true one-to-one calibration in there, but it's a good tuner's logic to use when looking at these ECUs. Now, what we're interested in here, obviously conscious of time, we're looking at the performance area of the ECU, and that's going to be towards the right-hand side of this table, or the last column that you'll see in the table. And that, of course, is because that's the highest amount of torque, or highest pedal input. That's where our maximum request is going to be, and this is where we see our highest air values. Now, these air values are cylinder filling values. That's basically how much air is being forced into the chamber, into the cylinder for each combustion cycle. And this is measured, as I said, as a percentage of air. On our axis on the left-hand side for our RPM, we need to pick a common denominator, like a point of reference we can use for each of the map tables. It's a really, really important key sort of takeaway from any of the training courses that we offer, that you are consistent in how you approach your tuning. There is no point in us looking at the values here at 4,000 RPM and then looking at a map such as our boost pressure limiter or at 1,500 RPM.
Makes sense.
The 2 points don't correlate. So we need to find that common denominator for the maps, And between 4 and 4,500 RPM for a gasoline turbo engine is a good point to look at, because that's typically where your peak torque, your optimum engine torque, is going to be produced. If you've got a naturally aspirated engine, the peak torque may be slightly higher in the RPM band, and of course it is all relative to the vehicle you're working on. If you're tuning a Ferrari or Lamborghini that revs to 9,000 RPM, well, we might start seeing our peak torque north of 5,500 in the ECU. So what I'm going to take away from here is the maximum value that's showing in the map table at this point. I'm actually going to write that down now. So I've got 4,000 RPM. I'm going to put the value down of 192% of air. That's really important for me because this is the request at this point. I need to see the difference between these values and my limiter values to understand what is left on the table, how much room, how much capacity there is there in the ECU for us to improve the performance of the engine. It's worth noting, and this is one of those really helpful hints and tips we cover in all of our training courses, both in-house, face-to-face, such as the one at SEMA, and on remap101.co.uk, where you can take the full Alientech ECM 3.0 gasoline tuning course at your own pace, not condensed into a 1 hour run through. Session. But we're going to look at the peak value in the table up here of 200%, because while that's not achievable at 500 RPM, I think we can all agree we're not going to hit maximum boost at 500 RPM. It is our first indicator of potentially more being left within the ECU for capability.
Understood.
So that's our requested engine load map. Again, a lot of maps inside of our air control, and a misconception is that our air control folder must control everything for our turbo then. It's all air-based. That's not the case. We actually have a dedicated folder in the driver for our turbo system. You see me scroll down here. So our turbo system on the screen now. The map I'm going to look at is a little bit down towards the bottom. If we follow the mouse down, we can see we have limiter of impulsive turbo pressure here. This is one of our biggest maps as a single row map. And by that I mean it's a something by one. See, a 16 by 1. If I open this map up, we can see it's a single column or single row map as we refer to it. This is our boost limiter. This is our main default go-to boost limiter for the ECU strategy. Now we saw there were 27 other maps in that folder. I'm sure you were counting them all on the screen.
It was a big folder.
There's a lot of maps in there, and they all have a specific purpose or need or requirement within the strategy. But the key thing we're looking for is our main default limiter. Again, similar to our diesel, we had a torque request and torque limit. On an air-based strategy on a gasoline ECU, we're looking for our requested engine load, and here we have now our limiter of impulsive turbo pressure, which is percentage of air-based. You see at the top of the screen. This is what's going to be limiting our boost pressure and our air inside of the engine itself. So if you remember, we wrote down 192% of air just from our requested engine load, and if we look at the same point at 4,000 RPM here, we have 172% of air. So already we can see there was capacity inside of the software, inside of the strategy on the stock software from the factory to potentially allow more performance. If those two values are almost identical, we'd have to look at other data points in the ECU, we'd have to do a lot of R&D and testing and start to push that car beyond the limits of the stock ECU data, almost into the unknown territory to try and get more performance. But the standard ECU leaves a lot of potential for us. Remember, this ECU and engine arrives detuned out of the factory, which gives us the option to restore that power back to it. So we can see that 4,000 RPM with 172% of air. You'll also notice on the screen we have multiple maps or multiple tables behind this first one. We actually have 6 of them grouped together. So effectively 6 limiter of impulsive turbo pressure maps. If I press enter, that activates the first map, and I can come in now and start highlighting, and if I was to the point of making modifications, I can make the changes here. We're not going to go through each of those individual maps in this session. In our course on remap101.co.uk, we go through why you would need to check all of these different map tables, how you would copy the changes from one table to another in a safe and consistent way. But for now, the values are the same on each of those tables, the other 5 that have come up on the screen. So I'm just looking at the values at the top here. So we've got a request and we've got a limit. We can see 192% of air is our request and 172% of air is our limit. Now, the fundamentals of a gasoline turbo engine, and any engine really, is we need 3 things to make our combustion. We need air, we need fuel, and what's the other thing?
We need spark.
Brilliant. are 3 things to make fire. So we've got our air request. Now, before we start looking at some of the nuances and some of the subtle maps that we may need to modify for our stage 1 tune to get the optimum from the engine, we need to look at those basic principles. If we've checked the air and we can see what we're asking for and what we're allowed to run, we then need to check our fuel and, of course, our timing. Now, the reason we're going to check those is not to see how many degrees of timing we've got or what the quantity of fuel is or what Lambda we're particularly running. It's to see if there is anything in those map tables that supports the amount of air we're trying to get into the engine.
Makes sense.
So the first thing we're going to do is look at our Spark Advanced map, as it's the middle of the screen now. Makes sense. We've got 3 or 4 different map types on here. We've got Spark Advanced Base, we have Minimum, and we have what's called our Optimal. We're going to look at our base map first of all. And as we open that map up, again, we can see we have multiple tables behind this one. And ECM is really useful for any tuner out there. When you've got multiple maps of the same type, ECM drivers group those maps together typically, making modification really easy and efficient for you. Making changes to one table can quickly be copied onto the others. But staying focused on the air quantity that we're looking for, if we check the axis at the top of the table, we can see it goes from 10% of air to 190% of air. Well, that's quite useful to know. Our standard car only does approximately 170. But our Spark Advance, if we look at the values, they do change in each column, so it's already been calibrated to run 190% of air. Oh, job done. The car can run 190% of air. It's one of the first things we look at to see if our Spark Advance, and of course our fueling in a second, supports that higher quantity. So again, I'll take a note. I'll write down 190% of air for my Spark Advance map. Not looking at the RPM values here, it's purely looking at the axis to see how much air is already calibrated into our Spark tables. Of course, a really, really crucial element of any gasoline engine tuning, whether it's turbo, naturally aspirated or supercharged, that we have the correct degrees of timing for the amount of air we're putting into the engine. Very quickly, as you'll see on the screen here, I'll just activate this map so we can highlight it. If we take the 4,000 RPM line and follow it along to the right-hand side, we can see as the air inside the engine increases, basically the pressure increases, the boost increases, the load on the engine increases, the timing decreases. When we have more force, more compression inside of that chamber, more air has been forced in there. When our fuel mixes with it, that combustion is going to be more volatile, it's going to explode a lot quicker, it's going to have more energy, so basically we don't need to ignite it as early. Well, if we're going from 170% of air to potentially 190, we can see the logic in the table follows that logic.
It's still there.
And it starts to reduce that timing in line with it. Really, really crucial.
So this map, in many ways, is ready done for you.
This map is
ready
told
done.
you
I can run more power, I'm ready to run more power when you make your other changes.
That is a really, really good observation, Paul. And it's what we saw in the diesel webinar as well. You'll see this in many ECUs. Now, turbocharged engines have a lot more on the table than a naturally aspirated engine, of course, because with a turbo, we can force a larger volume of air into the engine. With a naturally aspirated engine, it's all about optimizing what you've already got. So the gains aren't necessarily always as large. Some vehicles are an exception to the rule, of course, but with those naturally aspirated engines, it's more about optimizing small improvement in horsepower and a better throttle response and mid-range. You won't basically see as big a gap between requests and limits and so on in the tables. But with gasoline turbo engines and our supercharged engines, we have more to work with. Onto our injection system, we've checked our air, we've checked our spark. We now need the third thing to make a good combustion, which is the fuel. Now, typically, people go straight to the requested Lambda map. And if you've used different software, you'll see this as our open loop fueling or driver demanded fuel, even enrichment tables sometimes referred to as. This map here doesn't contain any information we need to verify or validate if we can run that higher percentage of air. This map is purely for controlling the fueling under those wide open throttle conditions. So it's a really important map that we need for tuning, but it doesn't help us at this point. So we close the map and we're going to look for our protection maps. And we can see here we have Lambda for component protection. It's also quite a big map in this whole sort of folder as well. As we open up our Lambda for component protection, we can see we have percentage of air across the top going from 10% up to 190% of air again. Now, I've just mentioned about the target fueling map. That's the one we need basically when we're on full throttle, open loop. That's the one we need for the performance. So why am I looking at a protection map? Well, it's fairly straightforward. The ECU has built-in protection all the way up to 190% of air to control the fueling to make sure it protects the components. So should something go wrong, should it see a temperature that's too hot from the EGT, should it even detect knock or whatever it needs to do, intake temperatures have gone too high, coolant temperatures gone too high, water pumps failed, whatever it may be, there are protection maps up to 190% of cylinder filling. So we've got Spark that says 190% of air, we have Lambda for component protection that says 190% of air, and we have a request map that starts at 190% of air, obviously in that last column. Everything's pointing us in that same direction, that we can unlock the potential of this ECU for a nice safe stage 1 performance tune, taking us from 170% of air up to 190%.
Yeah, nice increase.
So again, one of the biggest things when it comes to tuning, we're not suddenly giving the engine power that it wasn't designed for in the first place. We're unlocking its potential by understanding where the ECU is giving us the information that it can run further.
It's a nice way of putting it, because I think a lot of people say that. It's almost a marketing phrase. Oh, the engine's designed to do it, it's okay. We're not pushing things too far. But what does that really mean? Well, that is an absolute example of what you mean by that. The number is already in there. It's got all the backing data with it. We're just going to take it a little bit closer to it.
I couldn't have said it better myself. It's all about unlocking that potential that was already there. Now we can further validate this by going back to our very nice and simple turbo pressure folder, all those lovely maps for the turbo system, because there's a couple of extra maps in here that will basically quantify and validate those higher values. Now before I jump into them, I do want to just cover off a really, really useful, helpful hint and tip here. A lot of people always ask us, and it's probably one of the questions we'll get in this webinar, and we've had it before in courses, what does the percentage of air mean in real terms? Well, is 190% of air good? Is that 1 psi of boost pressure, or is it 1,000 psi and it's going to pull the engine apart and blow it to smithereens?
I don't know.
Well, I have an answer for you.
Excellent. I thought
there is a simple formula we can use. If we take that percentage of air, so 190% for those protection maps, if we take 70 off the value, there's a bit of maths here, so bear with me. This is why we said a pen and paper. If we take 70 off that value, it takes us to 130.
Yeah.
That's effectively the KPA, or the pressure we're running. Multiply it by 10, it's 1,300 millibar. If we take the stock value of 170 from our limiter, take 70 off gives us 100, times it by 10 gives us 1,000 millibar. Oh, it's the 1 bar of boost pressure the standard car runs. You can data log the vehicle and make a change to one of those limiter maps, maybe reduce it slightly and see the direct change you have in your boost pressure and work out your correlation between them. But we can use that simple formula of taking our cylinder filling on the Bosch ECU, take 70 away, multiply it by 10, and it will give you your typical approximate KPA or millibar of pressure that the car's running. Why is that important? Well, most of the maps inside of the ECUs, and even the latest sort of 2024, 2025 MG1 ECUs and CMOS ECUs, still have percentage of filling in many of the maps.
Okay.
So we're working almost on 2 measurement scales. We've got millibar over here and we've got percentage of filling elsewhere. Being able to convert that into a real world figure is very useful. So when we look at a map such as our turbo pressure HPA up here on the screen, we can see we have millibar on the screen. We can then relate our percentages of cylinder filling to the millibar maps. We can draw a comparison between the two. Now this map has a percentage across the top. It's our HPA. It's actually designed as an atmospheric pressure value across the top of the screen. However, as you can see, as we follow the RPM, every single pressure value at the top has almost the exact same column of values underneath. So basically that tells us that the top axis is kind of irrelevant. Right. The table is built with a lot of data and potential, but the ECU manufacturers decided, or the vehicle manufacturers decided, we only need this set of data in there. But what it shows us, and again, this validates that our tuning is going to be nice and safe and within the parameters of the stock ECU. If we're looking at taking our car up to maybe 190% of air, we just did the maths. That works out to about 1.3 bar, or 1,300 millibar. Well, we have an HPA turbo pressure map in here that's calibrated to 1,400 to 1,380 at that point. So again, we can see that the ECU is supporting these higher values, and there is even potential to push further if we started to move more into sort of the high-end stage 1, stage 2 area, if we wanted to start pushing a little bit beyond the edge of those maps. With data logging and time on the dyno, of course, we could look to do that as we have slightly higher values in this table. But staying on focus for what we're trying to achieve here is a nice, safe, smooth and progressive stage 1 performance tune using the values inside of the ECU itself. So that validates that we can push to that 190 nice and safe.
Okay. What else do we need to check before we can start cranking up things?
It's always running to the big numbers, isn't it? How do you give me more power?
Give me more power.
So our wastegate duty cycles, one more map we're going to check here. Now, of course, through our full ECM Titanium course on remap101.co.uk, we have 4 modules set up for our ECM gasoline course that take you through at a much easier pace and bite-sized chunks, allowing you to digest the information. We go through a large number of those maps, so almost everything in every folder, to explain why we'd need it, what its purpose is in the strategy, and the typical changes that we'd look to make. So that's broken down into 4 modules over 4 hours, and it's just £75 for each one of those. So it's priced very, very competitively to allow you to pick up this information in your own time. You can go back and rewatch them at any point. You're not having to quickly get all your notes down at the same speed that I'm telling you on the webinar now. But going into this one now, we have a wastegate duty cycle map, and again, it's another map that shows us HPA across the top and supported higher values. So again, with the right modifications to support the car, right intake, exhaust modifications, we can potentially run even higher than that 1.3 bar of boost pressure into our stage 2, running maybe 1.4, 1.5, or even higher. With these on a good stage 2 and looking at probably a high flow pump, we can quite happily run up to 1.6 bar on these engines without any internal modifications or forging. But at that point, you are really on the limit of what the standard turbo will do. So even with stage 2 sort of bolt-ons, still only about 1.4 to 1.5 bar as an absolute maximum. Your stage 1 with all stock components, 1.3 bar. The customer will be very happy with the performance gains, and reliability is still there, so it can still have its normal service intervals.
Safe, reliable, good tuning.
So as I said, there's a number of folders on here. Conscious we're now almost halfway through the webinar, and we'll get into the sort of meat and bones of it now and start making those modifications. There are a number of map groups in here that we just don't even need to change for a stage 1 performance tune, or even stage 2, such as our variable valve timing on this engine, so we can minimise that folder. We will make some changes to our rail pressure to help support those modifications we're making elsewhere in the ECU. But in things like our fuel pump, or standard fuel pump, we're not modifying that, so we don't need to change it. And on a stage 1, and this is one of the things about ECM as well, we actually have support for our stage 2 in here for high flow exhaust systems, for off-road and motorsport use, for high flow performance or even motorsport catalytic converters. We have the diagnosis switches in here, and for the rear or your secondary O2 sensor or third O2 sensor, depending on the setup on the car itself. But of course, not required for our stage 1 on there, no. So moving back up on our system. So the first thing we're going to go and look at now for our modifications is going to be in our air control, and it's going to be our requested engine load. So there's no point in putting anything up any higher if we don't change our request. If your limits sit above your request, then you don't actually have any limiters active and controlling the car. Now, the first thing a lot of people will say, well, that's great, I don't want any limitation. I can always see Paul going, oh, it's brilliant, all the power in the world. The problem with that is you actually have no control over the car and over the engine and the power delivery. If your limit sits above your request, then you're running purely on a demand-based strategy as opposed to a limited and controlled strategy.
Yeah, okay, I got that.
Effectively, if your boost goes above your request, it's an early lunch, everything turns off, it backs everything off because the job's been done. It's achieved its target. Suddenly the power drops, panic sets in, winds the actuator back up, trying to deliver the boost, and you end up with a horrible oscillation, this sort of on-off feel to the power. So we need to raise our request. If we agree that our new target is going to be 190% of cylinder filling for our limits, well then our request needs to sit above that. We could just take the value of 200% of air on the table that we've already seen here, but because we're raising the boost up a little bit more, we might have a little bit more of a spike in our boost, our overboost, which is a normal operating function of the engine. It's not a sign of bad tuning, it's a natural characteristic of how these engines work and operate, all turbocharged engines. We need to make sure that our request sits comfortably above our limit. If we work our calculations out, we know 200% of air, take our 70 off, gives us a 130 on there, so 1.3 bar, so we're quite happy at that point. We can put this up a little bit higher, and we're going to make a change by edit map, and we can put this up at 220 to keep it nice and happily out of the way.
Yeah.
It's not a value that's too high that's going to cause the ECU problems calculating. If we put 1,000% in there, yes, it's a great big number and it's way above our limit, but the ECU isn't going to really understand that value. It's not going to be able to achieve it, and you actually can have a problem the other way, where the ECU can throw limp codes or fault codes because it couldn't achieve the target that you asked for. Now, when you make a change like this, and typically it would be the last column only that you change, it's worthwhile checking in 3D. And this is one of the really, really useful things inside of the ECM Titanium software. By checking in 3D, we can see how that has affected, with the escape key, how that's affected the curve on the map.
I'm conscious of time, Simon. Why wouldn't we just start taking those changes in a little bit earlier, maybe at 80 or 70?
Exactly what I was going to jump onto now.
If I was about to tune, that's what I would do. I think, well, why just do the end flat out? Why not a little bit more on the way?
So if we look at the end, and again, this is coming back to our standard point of measure we were using, that consistent point. If we look at 4,000 RPM, it's 168% of air here. So we can see we could already achieve that on the standard car. Our limiter didn't kick in until after the 80%.
Okay.
And whilst we've only changed the last column, because of something the ECU does called interpolation, the ECU is actually averaging the values between these two cells anyway.
So it's not just black or white, one or the other. It's
so at 85%, we've actually raised it up halfway between these 2 points. 170 to 220 gives us about 195.
Right.
It's a good point though. So if you find you need the car to pick up earlier in a lighter throttle or loading condition, you can start to bring your changes in earlier in the ECU. But remember, all of this was fully achievable on the stock car. We're looking for the performance side. We're not trying to change the day-to-day driving when you're in traffic, in town, reversing the car in a supermarket.
Yeah, it's full throttle.
Yeah, it's the performance element is at its top end. The reason we check and validate in the 3D is to make sure that we don't have a very large spike and we're relying too much on the interpolation to average those values out. And of course with ECM, if we did have that, we could just select that last column, select in front of that last column, and we could raise the values up using our percentage key here, bring them up a couple of percent just to smooth out and make it a little bit more of a linear delivery.
Very nice, okay.
So it makes a little change to the previous column, not a huge amount, but just scales it up nicely. And again, you can double check your changes with the increase button to see the differences between the two. I'm going to save that, press OK. So that's our request raised. It's now a case of almost following that same investigation journey we did back through our modifications. So we checked our requested engine load first. Let's follow that down and look at our turbo system. And we're going to look at our limiter of impulsive turbo pressure. So that's that 16 by 1, which is our main default limiter. I'm just going to activate the map. I'm going to use one of the really useful functions inside of ECM Titanium. And I'm going to use the row column graphs button so I can see the map in both a 2D image and in the table form at the same time. This can often help you visualize the changes that you're making a lot better and how it's going to impact the vehicle itself. Now, without seeing this at the side, the temptation might have been to do sort of a diesel tune almost. We'd start at 1500 RPM, bring that boost in as soon as we can, and carry it on all the way through to our sort of peak torque. The problem is here, if you look at the standard build-up, it's quite smooth and progressive, has a spike up at 2200 RPM, and then no sort of linear dome or curve to it, it just cuts the boost. This is where understanding the vehicle you're tuning is so important when it comes to modifying any ECU. You need to understand how that car responds, how it reacts, ideally with data logging, or dyno time on the vehicle with data logging as well, or even just road time on there in safe control conditions, of course. Now this turbo is, I think it's the KO4 is the exact spec on this one. It spools quite hard, quite aggressive. If you try to bring that turbo in too soon, you can actually have something called compressor surge. That's when you can actually hear the turbo sort of spooling so hard and so aggressively that it can't actually get the air into the engine. That sort of sound as you're under load. Not to be confused with the old Skylines when you let go of the throttle and you hear chirping on the other side, which is when you've let go of the pressure. But this is on the spool up side. Compressor surge is not good for the engine or for the turbo itself.
Or for the turbo itself.
So again, we talk about consistency many times throughout our courses. We need to be respectful of what the manufacturer did with the software, because often they did it for a very specific reason. So we're going to be respectful of that, and our changes will start around about 2,250 RPM on this vehicle and build to our peak torque, which would be around 4,000 RPM. Now this is a little bit higher in the RPM band that we would typically start. It would usually be around 1,800 to 2,000 RPM on most gasoline turbo cars. But this is a great example to show why you may differ from those standard rules because of data inside of the ECU. So we're going to make some changes now with the right click function, and we're going to want to scale our modifications up. So we want to take our peak and have it at 4,000 RPM. That's where our peak torque is. That's where the best of the best on the engine is going to be produced. That's where we want our peak boost to be. But how do we know how much to increase it by?
10%.
The standard 10%. So we could put 10% on there, but then we could spend a lot of time fine-tuning and trimming and adjusting. It might not be enough, it might be too much. So one of the things we can do is just edit that one value to what we want it to be.
Okay.
So if we say 190%, we can then check the increase and say, hey, you had the right number, 10%. Whatever you're taking it up to at this point, use that method we've just shown, edit the one value and check the percentage change, because then, if you undo that value, you can make a nice, smooth, progressive change up to that point.
That makes a lot of sense. I get that.
So we're going to be 10% at the bottom. Make sure we press the percentage button on the interpolation window. Remember, it will remember the last settings you had selected. The bigger the change at the start, the bigger the kick will be on the car. We're actually going to go with a 0 at the start.
Yeah, I can see why you'd see that.
And we can see the changes disappeared off the top of the screen. Click our row column bounds button at the bottom to bring it all back into line. So now we're going to go from 4,500 RPM all the way to the end of the table. Now in a diesel, you may remember we did our ABC method. That's because we had quite a lot of RPM band with usable data after our peak horsepower.
Yeah.
So we gently brought it back down to stock. Gasoline engines, our peak horsepower is typically very close to our maximum RPM.
Yeah.
There is no safe real area to have that nice smooth progression back down. All we're going to do is put an artificial limiter almost on the car if we try to bring the values back down. So with a gasoline engine, it's areas A and B. In this case, it would just be a simple 10 in both boxes. And that just extends it all the way to the end. Now, of course, dyno time, data logging, validate those changes, verify everything's working how you expect it to be once you've completed the tune, of course. And if you want to push further, obviously you can. If you need to bring it back a little bit, you can as well. We often find on these vehicles, sometimes we'll actually reduce some of the stock boost low down to improve the life of the turbo, to reduce some of the wear and tear during that initial spool up. Something we do across a lot of the Volkswagen Audi group cars, even the Mark 8 Golf R, for example. So with our Katana Fire package on our Golf R, with all the bells and whistles, the exhaust system, intercooler, induction kit, and so on and so forth with the tuning, we actually reduce the torque load down by as much as 70 Newton meters on some of the maps to give a smooth build-up.
So you don't get a huge surge.
Yeah. You don't want it to do everything low down and then not be able to achieve it at the top end. We want to be smooth and progressive and kinder on the components, meaning we have a bigger horsepower output towards the top end. It's more usable, and as I said, it's easier on the drivetrain. When you're happy with your changes, close the map, and we can see here it's selected all 6 of those similar maps, and we're just going to copy the increments onto the similar ones, and we're going to use a percentage because that's how we've modified the map. If you change absolute, copy your changes across as absolute. If you do percentages, follow it in percentage. Again, consistency is the key when it comes to making changes to any maps inside of the ECU. Okay, so very quick whistle stop on there. We've done our requested engine load. We've got more air being demanded into the engine. We've done basically our default limiter on the ECU, and there's number of other limiters we can go in and make some little fine corrections and adjustments to based on live data and data logging on the vehicle. But for now, I want to keep it to those core maps that we looked at.
Yeah.
And we're going to go now to our fueling, not our Spark. We're going to go to our fueling next.
Okay.
There's a very important reason for that. We're going to leave Spark for one of our last map groups to change.
Okay.
And the reason for that is we already saw the Spark was calibrated to run a higher percentage of air, which means the values are already in the table for 190% of air. But also, the Spark Advance is one of the most powerful maps you have for making changes to the ECU, but also one of the ones that can have the biggest negative impact on the performance you're trying to achieve. Too much timing can cause the ECU to detect knock and detonation and start to pull the car back. Yeah. So a degree of timing in the wrong place can actually lose you 10, 15 horsepower or more, could lose you a piston. Yes. So we have to be very careful about any timing changes we make, and it is very specific to the vehicle, fuel grades, data logs, etc. So let's go and look at our fueling system first. And we're going to go into our requested Lambda map. I said this map is going to be important from our tuning side of things, for our performance side of things. Now, our Lambda, for those that are familiar, measured on here, Lambda, this is the O2 sensor in the exhaust, measuring the amount of oxygen in the exhaust. Our Lambda, our stoichiometric Lambda value here is equivalent for gasoline. So if this is a non-ethanol based car, non-flex fuel, this is going to be running Lambda 1 or 14.7 parts fuel, 14.7 parts air to 1 part fuel. Check that's an air to fuel ratio, not the other way around. Now, often you'll see people say, if we put more fuel in, we'll get more power. It's actually a bit of a misconception when it comes to gasoline engine tuning. The reason we run extra fuel through the tune is actually to manage the temperatures.
Yeah, keep things cooler.
Now, of course, we need a certain amount of fuel for the combustion. Remember those three things we need. If you take one of them away, like the fuel, air in a spark is not going to create any power. But there is a balancing point, an equilibrium. We run the vehicles richer, as you can see here, a value below Lambda 1 means we have a richer mixture than if we had a value above Lambda 1. The reason that we run the car slightly richer in these areas is to make sure that, yes, there's enough fuel in there for the performance we're looking for, but also we're not overheating the engine. Gasoline engines, one of the biggest barriers and headaches they have is thermal management. So you'll often see with a car where there's more fuel being put in there, it's not for performance gains, it's to actually manage the temperatures, which in turn actually lets you run the performance, of course. So, but of course, we don't want to put too much in there because too much fuel actually reduces the performance. It makes the combustion too cold and we don't get a good combustion. Ironically, the more gasoline we put in the fire, the colder the fire gets when it comes to tuning. So it's all about finding that sort of good optimum point for our air-fuel ratio. Now, every tuner will have a different opinion on this as to what their ideal AFR ratio is, that air-fuel ratio or Lambda value is, and it is really down to you to develop your own signature and style of tuning. We have some recommended values to start you with, but you may find on a certain application you need to run it a little bit leaner, or on another application you need to run it a little bit richer. Now, to be clear, that's not running the engine lean. We're just saying a little bit less or a little bit more fuel than the typical values you'd go to. So let's make our modifications in a similar area to where we've made our changes to our requested engine load and to our limiter for our cylinder filling. We're going to make a change to 2,240 RPM, 80% on our engine torque, and we're going to go to our interpolation. Now, on our interpolation, we've got the ability now to start reducing these values slightly. So if we're looking anywhere from around about a 5 to 6% reduction on our bottom right-hand corner, that's going to take us down to around about 0.86, 0.87 stoichiometric value, so on our Lambda, which is about 12.7 AFR for those that are working in AFR scale on there. You can just set this whole area to a block change. So the whole thing you could set as -4, -5 in this area, even -6. But a scaled approach to it is ideal to start with. Data log, test, check on the dyno, and make further changes if you need. So we can see there we're coming down to 6,500 RPM, 0.86 on our Lambda, which again is going to be about 12.6, 12.7 air-fuel ratio. And it's progressively getting a little bit richer. Why? Because our temperature is getting hotter and hotter the higher we rev. Close the map. and we will copy our changes. We did percentage, so we'll copy them onto the similar maps behind. Of course, remember, on our course on remap101.co.uk, we take you through why you need to check those similar maps each time to ensure you are making the right changes to the right data that you expect to be there. We have Lambda for component protection. I'm only going to look at one of these because there's two to look at, and conscious of time, there's only 15 minutes to go, and there's quite a few more maps we need to look at for this tune. Our Lambda for component protection is one that's often overlooked. We've just made the ECU a little bit richer, so you'd think, well, our protection map, that's good, it's really rich, it's nice and safe for the car. The problem is, anyone that's ever dynoed a car will know that even on the standard car, the target lambda it's trying to run in around lambda 1 to start with, by the time the boost kicks in, the ECU doesn't gradually make itself a little bit richer and a little bit richer. It goes, oh, this is a bit warm, the temperatures are increasing quickly, so before any issues occur, before any thermal incidents occur with the drivetrain, it jumps straight to the protection map, which is great for keeping everything safe, but it squashes our power, it restricts us. So one of the best things we can do in here, and one of the real sort of secret things when it comes to tuning, is to actually adjust these values. And it is only in this bottom corner here where they've gone a little bit too rich for what we're looking for. We can lean them out slightly, and we can basically reduce that operating difference, if you like, between our target lambda and our protection. By having them operating closer together, there's less oscillation between the two, they work more harmoniously together, and we get a more consistent result from the vehicle. So on this particular one, it's going to be quite simple. We're going to bring this up to 0.81 as our lowest value, and we do that by just editing some of the values in the table here. So we have 0.81 for those three cells, and anything that sits below 0.81 I'm targeting here to just raise the values up. So it's quite a small change. But it just means under those conditions, especially the higher RPM where we're really looking for that last final few horsepower, if it suddenly jumps into the protection map, we're going to lose 10, 15 horsepower. And you're going to be chasing the tune, and importantly, you're going to start making overcorrections into other maps to try and desperately get that number on the dyno to make the customer happy. And then you start making changes to maps that don't need to be touched.
Start adding more fuel, adding more boost pressure, and still you're not going to get there.
You're just fighting the strategy within the ECU at that point, and all you're doing is actually almost making the situation a little bit worse. So there are two main maps in our injection system. Let's minimise that one down for us for a second, and that takes us into our spark advance area. Now, typically for a stage 1 performance tune on an engine like this, we don't actually need to make any changes to our spark advance, but for those that aren't tuning gasoline engines, I will cover off what we would typically do for a spark advance change. So there's something for our NA friends, something for our supercharged friends, and for our turbocharged friends. The logic between these maps in here, remember we've got a spark advance base map, minimum, and our optimal. The easiest way to look at this if you're new to tuning is to approach them in this way. Our minimum is basically our lowest spark value. Makes sense, it says minimum. Our spark advance base is effectively our default. That's our starting map, not for cranking, but our default spark advance map. So normal conditions, this is what the car's running as a starting point. Our optimal is the ideal. That's the maximum amount of timing to achieve the maximum amount of torque in an ideal world with all the conditions perfect, racing fuel in the engine, outside temperatures minus 10 degrees, super cold air intakes, it's all wonderful and all great. Unfortunately, not many cars run in those conditions with race fuel, and of course, as soon as you start accelerating, intakes go up, engine temperatures go up, etc. So it's the base map that we actually look at when it comes to normal tuning. You'll see if you ever compare the base map against the optimal, and we do go into this in much more detail on our Remap 101 course for ECM Titanium, on our gasoline course, about the logic between these maps, why you would modify certain maps in certain ways, and sort of the tuning tips of the do's and don'ts and best practices for making these changes, especially when it comes to things like the optimal and the minimum maps. But for our default sort of approach to tuning, we're going to be looking typically at our positive values in the table. One of our golden rules is we don't really want to change negative values, not for performance tuning anyway. That's only when you start doing things like your pops and bangs and overrun, then we do need to have negative values for our timing. So we're going to look at our positive values, which will be typically down in this corner. Don't be tempted to just blindly follow the logic of, well, I made a change at 2000 RPM on one table, so I must change every table at the same point, because you then risk making changes to values that could have a disastrous impact on the vehicle, really sort of catastrophic failure points almost.
Okay, let's not be doing that.
So when it comes to timing on a gasoline turbo engine, it's going to be very small changes, maybe half a degree or a degree at most in this bottom right-hand corner of the table, just as that final sort of extra tweak to the map to get the best out of that stage one. It's got to be running on really high octane fuel and in good operating conditions with a good sort of service history, if you like, on the car. If it was a naturally aspirated engine, we'd typically be looking around about 3 degrees of timing, and similar for supercharged engines. And we'd be looking at a slightly broader area of the ECU table to make those changes on. Because with our naturally aspirated engines, and to a degree our supercharged ones, timing is one of those key factors to get us that power, to control how much additional power we can have. One of the things we'll look for, and I'll just show you here, now this is not where we would go, of course, on a gasoline turbo, but showing you for our NA and even our supercharged engines, we're looking for a wider area of the table, and we're looking for where our values have a nice clear drop. So effectively, where we've got high values consistently and then they drop a good 2 or 3 degrees for the rest of the table to carry on. That gives us a nice area to make a modification while still maintaining the same strategy and logic to that table. What we don't want to do is, for example, make a change here where we put 3 degrees on and suddenly the button. Oh, hang on, I'm in the wrong thing with numlock pressed on here on the screen. We put 3 degrees on here, and now suddenly we've got values that are decreasing and then suddenly increasing again.
Yeah.
The logic as the load increases on the ECU is that the values should be decreasing, the timing values should be getting lower as the load in the engine increases. So whilst we can raise these values, we want to keep that same logic to the table.
So very small changes, really.
Very small changes, yeah. And it is very much a case of less is more with timing. Start small, you can always add more. Add too much on the very first go, and it's very hard then to correct that change if it's caused a mechanical failure on a part.
Yeah.
So start small, log, check, repeat the test with a little bit more timing if you need to. The reason we have things like the minimum spark advance maps in these drivers is because of things like the pops and bangs.
Yeah.
Where you would need to not only reduce the spark advance base map in certain areas, typically in these areas on the left-hand side of the screen, retarding them down to like minus 20, minus 30 degrees, depending on how aggressive you want the overrun to be, igniting the fuel effectively almost on the exhaust stroke. But if you don't change the minimum, if we've set our base map to minus 30 here and we haven't changed the minimum, well now suddenly we're actually running 12 degrees or 13 degrees of positive timing. So all those changes you made to try and make the car do those burbles and overrun sounds has now been wiped out by the default minimum value. So again, doesn't matter what tuning you're doing, whether it's for wonderful tuning for car parks, making the cars pop and bang for off-road shows and so on and so forth, or you're going for performance, consistency is key. You have to understand the relationship between those different maps to understand the impact that changing one of them will have upon the others. Okay, so we've covered off how we make changes to our spark system. Conscious we have 7 more minutes to go. I'll just look at Gavin, see if he's got any questions in the meantime over there. He's just checking through the chat now for any.
Bamboozled everybody. There's no questions. That must be a first. Just out of interest, I mean, we've seen the type of changes you'd make there on this stage 1 map. What sort of power is that likely to develop? Because some of those changes looked quite small. I'm sure there are people watching thinking maybe we've gone too tame.
Yeah, it is, as I said, a very safe, smooth, progressive stage 1 tune on there. I mean, that's going to give us, in terms of our boost changes and things, we're going probably looking at a good 30 horsepower increase.
Okay.
There is more, and this engine can quite happily up to 50 horsepower gains, but it is dependent on so many factors. If you just jump straight in with bigger changes and you're running on poor fuel, you're going to end up with knock, detonation, have problems with the cylinders. If you're not able to data log and you're running in hotter climates, the car is going to be over-fueling, trying to compensate for the temperatures, and it's going to be down on power as well. Yes, with a dyno, you can push further, and it's something we talk about in our classroom courses and our online course on Remap 101. This is showing you how you can take in a very short space of time, 45 minutes I've been talking for now, how you can take some of the standard values in the ECU and open it up and optimize it for a stage 1, a safe stage 1 tune. Yes, if we start to look towards our stage 2, we can push further on the boost. As we mentioned early on in our investigation phase, there are values that do support a higher level of tune on here. However, the important thing to look at is, to go back to our spark advance, as soon as you go beyond 190% of air in this engine, you're off the end of the map. Now, our diesel webinar last month, you'll have noticed we had all the capacity we needed within the standard axes.
Yes.
So we could max the car out on stage 1, even stage 2, with those standard axes.
So what would the strategy be here?
The strategy here would be, we would then, if we went to 200% of air on our limiter, we would then have to data log and potentially reduce our values here to compromise the table at this point to make sure it's safe for 200% of air.
Okay.
Or we could then move into our more intermediate and advanced strategy of starting to make changes to the axes and start to scale the axes up.
Right.
So this is another sort of, it's an advanced technique really, where you sort of get into your stage 2 and 3 tuning, where we start to modify the axes. So with our interpolation here, we could actually put our numlock on, put 15% in here. We could scale our axes up. So now the table recognises up to 218% of air, or whatever it may be. But
so
that
you've literally changed the format, not just the format, but the actual base of the data.
Now we've changed the logic in the ECU, the strategy of the ECU, but this has a knock-on impact because not all of the tables have now been scaled to the same point.
And this is the difference when you start getting into quite heavily modified vehicles and really
heavily modified vehicles,
2.
And really pushing the maximum of the standard components on there. Can be done without making changes to the axes, but it does require data logging and validation of the changes to ensure that the car is running safely under those conditions. And of course, by doing that, we've now had the impact of making this column here effectively 190% of air.
Yeah.
Well, that's had a big increase. That's put the values up 50% here for timing.
It really is quite a dramatic change once you start.
Yeah, just by changing an axis, that can have a huge knock-on effect, both for positive and also for negative impact on the engine itself.
Very conscious of time. We're running towards the end of the session. I hope people have really enjoyed that. There's been a lot to cover there, more maths I think than in the diesel, that was for sure. This session is obviously going to be on YouTube tomorrow, so you can dial in and watch it again. I know Simon has endlessly been plugging our online courses, but they are actually crammed full of this information. And again, you can watch them again and again to sort of cement that information in. I see we've just had a quick question come in there. Gavin, question master?
Yeah, the question is from Maths UK. If you were to change the axis larger, stage 2, would you extrapolate the table to maintain same logic?
The axis larger?
Yes, as you've just shown.
Oh, the axis, sorry, the axis larger. Yes, so you could extrapolate the data on there. So effectively, if you were doing, spark advance gone? Yes, you could apply the logic that's there. So what we've done we would then effectively then have to start making changes to the previous columns to bring them in line with the logic and strategy of the ECU. So some people do this even in Excel. They'll actually build a table in Excel and start making the changes in there. And obviously there's other softwares and things you can do that with, but we can start to make changes here. So effectively take these values and put them into this column, meaning that we do have control for the correct values at 190% of air.
Yeah.
But again, it depends on how much scaling you've done to the axes and what the overall target is. Again, for stage 1 tuning, even stage 2 tuning on an ECU like this, scaling axes isn't typically required. It's not a normal thing to go to. It's only really when you've hit some sort of limit, ironically with an ECU, a limit in the software, but a limit that you can't get past, that you then start to make that change. So you've then got the control over that higher value that you're looking to run.
Okay, great. I hope that answered your question. For our next session coming up in November after SEMA, we'll be doing this probably around the 20th of November. That date's not been set yet. We're going to look back at EVC Winnow software. So we're going to try and repeat what we've done with the gasoline and the diesel files that you've seen in ECM, but move on to Winnows. But before we do that, we're going to start with map pack building. So how do you build a map pack in Winnows? So we don't obviously want to be buying these all the time. They're expensive. So we'll talk a little bit about constructing a map pack, how we approach doing that. And once we've done that, in the sessions that follow, we're going to go on to write a stage 1 map in Winnows for diesel and then repeat that again for gasoline. So we've got the next couple of sessions lined up. We're going to take a switch from ECM and move to WinOLS. I see Question Master has just let me know we've got another question in. Gavin, next question, please.
Yeah, this is from Toon. Do the new courses also cover torque bases, ECUs?
Yes. Yes. So the new course we use for the ECM course, It has a MED17 ECU in there. The MED17 Bosch ECU has both strategies in. So the reason that was chosen because it covers obviously both elements in there. So it doesn't focus specifically on air-based, doesn't focus specifically on torque-based. It covers both in there. But again, I know the couple of things we've covered here with the requested engine load, for example, the logic is still the same logic when you're working on a torque-based or almost solely torque-based strategy ECU. Instead of having percentage of torque, you have Newton meters across the top of the map. Instead of having cylinder filling as a percentage, you actually have a measurement of air quantity in the map table. So the map table is still doing the same thing, just the values are actually not percentages, they're real world measurable values. So the logic is still the same, it's just the values inside the tables have changed a little bit. And of course it will adjust slightly from ECU to ECU, from ECU manufacturer to each, but ultimately a 2 litre turbo engine, whether it's got a Bosch, a Siemens, a Marelli ECU or whatever it may be on there, has to function a certain way, has to run a certain amount of boost typically, a certain amount of fuel and a certain amount of timing, because a 2 litre engine is a 2 litre turbo engine.
And I think it's worth saying, the courses that we're developing, the online courses, a little bit like these sessions, they're kind of live animals in many ways. If you're seeing something that's frustrating you out there that you don't understand how to do it, we will write a course for you. You can't be the only one that's struggling with that. So we've just launched a whole range of new ECM courses. We've got some more advanced ones coming, and I think we're currently working on Swifttec as well. Is that right?
Yeah, we've got Swifttec courses in development at the moment. Obviously, I think we mentioned our last webinar, our StageX beginner courses have gone live as well.
But they're only the beginner courses. We've got some more advanced courses
ones
coming
on the way,
too.
yes.
So if you have got things that are frustrating you and you really would like a course to cover some of these things off, get in touch and we'll try and put that together for you.
Yeah, we'd really love to hear that, to be fair, because it's you out there in the industry doing this live on vehicles, as we do. As we just finished an XKR on the dyno just before we went live for the webinar today. We're working on vehicles. We see these frustrations on certain vehicles and ECUs as well. You must all see certain frustrations or logics that you're not quite familiar with or stuff you'd like to know more. Let us know and we can put those courses together. It may even be the topic of a webinar.
Same thing. If you've got a thing that you want us to cover in these webinars, email us in and we'll try and do just that. I think that probably covers everything we need to cover tonight. I'm sorry it's a little bit rushed at times there, but there's a lot of maps in there and we had to cover a lot of ground. I hope you can come and see us at SEMA. We would love to see you. So SEMA opens 1st of November, 2nd of November? 2nd of November, I think it is.
Monday.
The Tuesday.
Tuesday, yes.
Tuesday. I've just been corrected. It's the 4th. We'll be there wherever it is anyway. So SEMA, first week in November. Would love to see you there. Of course, email us in the meantime if you've got any questions, and this video will be live on YouTube as soon as tomorrow. And if we don't see any of that happening, we'll hopefully see you for the November webinar. Cheers, guys. Good night.
Thanks, everyone.